This sphere is falling through a liquid at constant speed, with both upthrust and viscous drag acting upwards. Neither force on its own has to equal the weight, but together they do. Pressure is a force acting normally on a surface divided by its area. In a stationary liquid, pressure at a point is the same in every direction and increases with depth. A liquid column with area A and height delta h has a weight ρa∆hg. In equilibrium, that weight is supported by the pressure difference. Divide by A, the pressure at the lower level exceeds that at the upper level by ρgΔh. Place a block of height ΔH in the liquid. Forces on opposite side faces cancel. But the lower face is pushed more strongly than the upper face, so the resultant upthrust is the pressure difference multiplied by the area, ρgΔHa. Since ΔH times A is displaced volume, the upthrust is fluid density times the displaced volume times g. Archimedes' principle says that upthrust equals the weight of the fluid displaced. A freely floating object settles when upthrust equals its weight. That is an equilibrium condition, not the definition of upthrust. A fully submerged dense sphere can have less upthrust than weight and still sink. Dynamic viscosity, eta, measures a fluid's resistance to adjacent layers moving past one another. Upthrust exists at rest. Viscous drag, however, requires motion relative to the fluid. For a small rigid sphere moving slowly in creeping laminar flow, Stokes' law gives the drag magnitude as 6 pi eta rv. It acts opposite to the relative velocity. The SI unit of viscosity is the Pascal second. For the same sphere at the same speed, a larger eta produces more drag. This is not a general drag equation. Once inertial or turbulent effects matter, or nearby boundaries alter the flow, Stokes' law needs a correction or a different model, and most of this is above A level. The earlier drag lesson showed how terminal speed is approached. Here we begin after the acceleration has ended. The sphere is still moving, but its resultant force is zero, so weight equals upthrust plus drag. We use this balance to measure viscosity. Let's use a tall, wide, transparent tube. Measure the sphere diameter in several orientations with a micrometer, and then halve the mean for the radius. Measure or obtain both densities and record the liquid temperature. Now release the sphere, centrally without pushing it. Put the first marker well below the surface after terminal speed has been reached. Measure the marker separation and travel time. It covers 0.109 meters in 10.0 seconds, so its terminal speed is 0.0109 meters per second. Combining the force balance, sphere volume and Stokes' law gives us eta equals to 2r squared g times the difference between sphere and fluid densities, all divided by 9 times the terminal speed. So if the radius is 2.50 times 10 to the minus 3 meters, and the sphere density is 1800, and the difference between the sphere and liquid densities is 800 kilograms per cubic meter, both 3 significant figures, substitution will give us 1.00 Pascal seconds. If you set drag equal to weight and omit the upthrust, you get 2.25 Pascal seconds, more than twice the correct value. Confirm equal times over consecutive equal distances and then repeat. Keep the sphere clear of the walls and bubbles, and the temperature steady. Continuing acceleration or wall drag makes the measured speed too low and the viscosity too high. For most liquids, warming lowers the viscosity. Pressure differences produce upthrust. Relative motion produces viscous drag. At terminal speed, weight equals their sum. Next, we leave materials and ask what progressive waves actually transfer.